Alright, hi guys. So before I go on with this example, I just want to point out that the purpose of these calculations of the electric fields is not to memorize them or know what they are, but rather the process of getting there. So there is no need to memorize what the electric field at a point P away from a charged hoop or a charged rod. Like, you do not need to know that. You just need to know the process and the thinking behind how we get there. And without further ado, I will go into this. So here we have a uniform rod, and we put a charge Q on it. Its length is 2a, and if we take a small section of this rod, it will be a length of dy and have a charge of dq. This will be important for the integration. Here's our y-axis, upward, and then here's our x-axis. We're going to call our length from our rod to the point P x, and we'll call the length from the origin to dy y. Alright, so if we had an electric field vector from this point go towards P, we'll notice that there would be an electric field in this direction. So therefore, if we draw the components out, we get the electric field in the x direction and the y direction at this point P. Another thing to notice is that r is going to be the distance from here to here. Remember that electric field is a distance from the point, from the 2 points. So from here to here is r. And r is, using the Pythagorean theorem, x squared plus y squared, and the square root of that. Last thing that is important is linear density. So there are different types of charge densities that we use in electromagnetism. This one, lambda, represents linear. Sigma will represent the area, so how much charge is on a square or a circle, and rho will represent volume, so how much charge there is on a cube. Units are coulomb per meter for linear, coulomb per meter squared for area, and coulomb per meter cubed for volume. In this example, since we're dealing with a rod, we only need to worry about linear density. So linear density is just the amount of charge on the rod divided by the total length of the charge. In this case, we have a charge Q, and the distance from this end of the rod to the other end is 2a. So therefore, linear density is 2a. Now, I actually screwed up while doing this video, so I will use the same work I did, just not write it down. So we're going to first begin with writing our electric field equation. So we know that dE is equal to k dq over r squared. We already defined that. Now we know that our charge kind of varies with our distance, right? So we can say that the charge is going to be equal to our linear density multiplied by the change in y. And if you notice, units cancel out because it's coulombs per meter, and that's just meters. So if we simplify that out, we get q dy over 2a. Now we can go ahead and plug that into the equation. So dE equals k lambda dy over r squared. Notice we plug this in for dq. And I further substituted with kq dy over 2a over r squared. Alright, now to find r, we need to solve, we know what r is. It's going to be square root of x squared plus y squared. We want to get this in variables that we can use. So in this case, we want to use the variable y, so therefore we're going to use x squared plus y squared. So we're going to plug that in, which I did here. And now we can't find the electric field just from here. We need to split this up into its 2 components and then integrate from there. So we need to solve for y direction and x direction. The y direction is simply sine alpha. So the electric field times sine alpha will give us the electric field in y direction. Now since alpha is going to change and we don't want to use another variable, we're going to solve sine alpha in terms of x and y. So we know that sine of an angle is equal to opposite over hypotenuse. So here our opposite is y, and our hypotenuse is r, which is equal to the square root of x squared plus y squared. So if we just plug that in, we get our equation from here, dE times sine alpha, which is y over square root of x squared plus y squared. Same thing with cosine. The only difference is it's adjacent over hypotenuse, so it's x over x squared plus y squared. Alright, from here we want to integrate from negative alpha to alpha, since we are integrating with respect to y. And a note that I should bring up is in the last video when we were dealing with our charged hoop, I said we can assume that any vector that's perpendicular to the x direction will be cancelled out by other vectors because it's a circle, and if you think logically, the two vectors in opposite directions will cancel out. Now I can say the same thing here, that if I have an electric field line in this direction, I should have an electric field line in this direction also, in which the y vectors cancel out. However, I will go through the proof of that to show that the vectors really do cancel out. So if we're going to take the integral of our electric field, we're going to go from negative a to a of kqy dy over 2a x squared plus y squared, quantity 3 to the halves. And that's just multiplying this out here. So in this equation, we know that kq over 2a is going to be a constant, and then y dy over x squared plus y squared to the 3/2 power is going to be integrated. A quick thing to note is that x does not change, so therefore we can treat x as a constant, and we can safely integrate using one variable, which is y. So the integration for this one is going to be a u substitution. We're going to set u as x squared plus y squared, and we're going to set du as the derivative of that, which is 2y dy. And then we're going to go ahead and plug this in to this equation. And after we're done, we get our integral, our integral, which is negative kq over 2a multiplied by u to the negative 1/2, and we're going to go from negative a to a. So I'm going to plug in u. If you notice here, we had u to the negative 1/2, so I'm just going to plug in u, which was x squared plus y squared, and then we're going to solve this out. Kq over 2a, and if I plug in negative a for y squared, we just get a squared. If I plug in a, we're just going to get a squared. So if you notice, we get the same term, and since these two, when added together, cancel out to 0, we can therefore conclude that our electric field in the y direction is 0. So here, again, this is the proof to what we assumed beforehand, and it's pretty handy because each and every time when you see an example like this, if you can notice some symmetry to a problem, you can automatically assume there's no electric field in that direction. So pretty useful. This is the proof to that. And continuing on, here's the electric field in the x direction. Nothing new, just kqx dy over 2a quantity x squared plus y squared to the 3/2. This portion is again a constant, and then this one again is an integral. This integral is a bit more complex, and you won't need to know how to integrate this specific form on the AP exam, so don't worry too much about it. I'm just gonna skip ahead to the bottom and say that our integral, after solving it out, is kq over x times the square root of x squared plus a squared. So again, don't worry about how we got there. It's just integration and simple algebra. Anyways, so this is the electric field in the x direction for a uniform rod. And if we notice, there's only an electric field in the x direction, so therefore our electric field for this rod is equal to kq all over x squared plus a squared, and it's in the x direction. Alright, so we have to do some evaluations and ensure that we did this correctly. So our first thing to assume is, let's assume that this rod had basically a length A of nearly 0. So in other words, let's assume it becomes a particle. Well, if it has no radius, then electric field is equal to kq over x times the square root of x squared plus 0. And if you simplify that out, you get kq over x squared, which makes sense because if we define this distance x, then it works out. E equals kq over r squared. Matches. Alright, the second thing we should do is actually solve in terms of linear density. So, if this is our equation, we know that linear density is equal to q over 2a. So, I'm going to rewrite this here. kq over x. And what I'm going to do here is I'm going to factor out an a from here. So, if I factor out an a, then this is going to be x squared over a squared, and then plus 1. Now, if we want to solve for this, we need to multiply each side by 2. So 2 lambda equals q over a. And if you notice, q over a is here. So we can just plug in 2 lambda there. So electric field is equal to 2k lambda all over x times x squared over a squared plus 1. Now we're going to assume one more thing. Let's assume that our rod, instead of having a length a, instead goes off to infinity. So we have an infinitely large rod. So therefore, if a goes to infinity, this x squared over a squared terms goes to 0. So our electric field then, therefore, is going to be equal to 2k lambda all over x. And then if we think about it, if we have an infinitely large rod, it really doesn't matter whether or not the r's are all this way. Like, it doesn't matter if it's like this or like that or like that. In reality, it's going to be always our electric field is always perpendicular to this point. So therefore, instead of writing x, we can therefore now write 2k lambda over r. And although it doesn't seem that much of a difference, the x here represents in the x direction, whereas r represents the point on the rod to our point P. So here is the electric field due to an infinitely large rod. Here's the electric field due to a finite rod, and then the electric field due to an infinitely small rod is, of course, kq over r squared.